Section 14.3 talks about apportionment methods, and there's going to be 4 different kinds of apportionment methods that we talk about. Basically, apportionment is just how you adequately or fairly allocate resources. So the example we're going to use over and over again is the House of Representatives. But it could range from anything. For example, how many police officers does one precinct get in a certain city? How many nurses should go on a certain shift based on need? So that's what we're going to talk about today. So the goal of apportionment is to determine a method to allocate the total number of items to be apportioned in a fair manner. There's 4 methods we're going to talk about today: Hamilton, Jefferson, Webster, and Adams. First thing you have to know how to do is how to calculate the standard divisor. To obtain the standard divisor, when determining a apportionment, you use the following formula. You take the total population and you divide that by the number of items to be allocated. To obtain the standard quota, when determining apportionment, take the population for the particular group and divide it by the standard divisor. So let's look at an example really quick. Determine the standard quotas for clinics B, C, D, and E of the First Physicians Organization and complete the table below. Use 18 as the standard divisor. Now, they didn't tell you this, but I'll go ahead and tell you. There was a total of, the way they got the 18 was the total number of patients they had was 1,080, and this particular firm only has 60 doctors. So if you took 1,080 and divided it by 16, that's where they're getting the standard divisor of 18 from. Okay, now they want you to find the standard quota for each one. So the way you get the standard quota is you take the number of patients and you divide it by your standard divisor. So if you take 246 and you divide it by 18, you will get the 13.67. So on this slide, I've gone through and I've done all the divisions for you. 201 divided by 18 is 11.17. 196 divided by 18 is 10.89. 211 divided by 18 is 11.72. And 226 divided by 18 is 12.56. Now notice if you take your 1,080 divided by 18, or if you added all of these together, you would get 60.01. That's a little bit of a problem because we only have 60 doctors. You're not going to have a 0.01 of a doctor. And so sometimes that can cause a little bit of an issue. So the lower quota is the standard quota rounded down to the nearest integer. The upper quota is the standard quota rounded up to the nearest integer. So say, for example, our standard quota was 13.67. Our lower quota would be 13. Our upper quota would be 14. So Hamilton's method uses the standard divisor and the standard quota. So to do Hamilton's method, the first thing you have to do is to calculate your standard divisor, and remember that's the total population divided by the number of items to be allocated. Second step, you need to calculate each group's standard quota. So to do that, you take the population of each group divided by the standard divisor. Then on Hamilton's group, he rounds each standard quota down to the nearest integer. So he does not follow traditional rounding rules, he always goes down. Initially, each group will receive its lower quota. Sometimes you're going to have some leftover items. When there is leftover items, you are going to distribute the leftover items to the groups that have the largest fractional parts until all the items are distributed. So we're going to use Hamilton's method to distribute the 60 doctors to the First Physicians Organization that we talked about in example 1. So remember, when you look at this, we went through, we found the standard quota for each of the doctors. So Hamilton believes that you should always round down. So initially for group Clinic A, he's going to give them 13 doctors, Clinic B, 11, C, 10, D, 11, E, 12. Now notice he's only used 57 doctors here. Okay, so he had 60 doctors, so he has 3 left over. So then what he does is he looks for the items that have the highest decimals, and he gives them the extra doctors. So the 13.67, the 10.89, and the 11.72 had the highest decimal parts, so he goes ahead and gives them the extra doctor. And so they'll have, so if you add them all together now, you add up to be exactly 60. So this is the Hamilton method of apportionment. The quota rule. An apportionment for every group under consideration should always be either the upper quota or the lower quota. So Jefferson's method is a different version of apportionment. And on Jefferson's method, he determines a modified divisor D such that when each group's modified quota is rounded down to the nearest integer, the total of the integers is the exact number of items to be apportioned. So we will refer to the modified quotas that are rounded down as modified lower quotas. Now, as far as calculating that modified divisor, it's kind of a guess and check method. You just have to keep trying it until you find one that works. There is often more than one that will work at a time. Once you've found the modified lower quotas, you can just apportion each group its modified lower quota. So let's look at an example. The Republic of Geranium needs to apportion 250 seats to the legislature. Suppose that the population is 8,800,000. There are 5 states, A, B, C, D, and E. The 250 seats are to be divided among the 5 states according to their respective populations given in the table. Use Jefferson's method to apportion the 250 legislature seats among the 5 states. The standard divisor is calculated to be 35,200. Okay, so that 35,200 came from taking the population, 8,800,000, and dividing it by the number that needs to be apportioned, which is 250. So if you're wondering where that number came from, that's where it's from. So now, if you were doing this with the Hamilton method, which we just did, you would take each of those populations and divide it by the standard divisor. We're going to do Jefferson's method, though. So with Jefferson's method, the modified quota for each group needs to be a little bit greater than the standard quota. So the way to get this done is to use a modified divisor, not your standard divisor. Your modified divisor needs to be slightly less than the standard divisor. Well, we know our standard divisor is 35,200. So we want to try something that's a little bit smaller. How much smaller? We don't know. It's trial and error. So we're going to try 35,000. 35,000 is slightly smaller than 35,200. So we're going to say that our modified divisor is 35,000, and then we're going to go through to each state and take its population and divide it by our modified divisor. And then when we get that answer, we're going to round down to the nearest integer and use the lower quota. So I've shown this done in the next slide. So the first one shows what would happen if you divide by your standard quota, the 35,200. Then I went through and I divided by the modified quota, 35,000. Then I went and I used the lower boundary. So I took my 26.88 down to 28, 35.1 down to 35, 142.59 down to 42, 23.23 down to 23, 21.84 down to 21. Then you want to add them all together to see if they add to be the exact seats you need. Well, they don't. We needed 250, and when I add these together, I only get 249. So that means I didn't pick an appropriate modified divisor. So this time, I'm going to change my modified divisor. 35,000 wasn't small enough. So this time, I'm going to take it down a little more. I'm going to try 34,900, and I'm going to go through and take each population divided by that amount. So this time, when I divided, I got 28, 35, 40, 143, 23, 21. And notice that this time when I added it up, it did add up to be 250. Now, did I have to pick the modified divisor, 34,900? No. Could I have picked 34,800? Possibly. You have to run through the experiment and see if when you add it up, it adds up to be 250. So this is going to tell you how many representatives each state gets based on the Jefferson's method. So the sum of the modified lower quotas is 250, which is our desired sum. So each state is awarded the number of legislative seats listed in the table under the category of modified lower quota. The third method we'll talk about is Webster's method. When you use Webster's method, you also have to determine a modified divisor D. But this modified divisor is one that's rounded to the nearest integer. So the total of the integers is the exact number to be proportioned. We will refer to the modified quotas that are rounded to the nearest integer as the modified rounded quotas. Once you have this figured out, then you'll apportion each group its modified rounded quota. Okay, so let's use the same problem we did before. We've got the Republic of Geranium. We have 250 seeds to spread. Their population is listed in the table. The standard divisor was 35,200. So what we're going to do is we're going to round our standard quotas to the nearest integer. If we used the standard divisor, our standard quotas were 28.5, 34.9, 141.78, 23.10, and 21.72. So remember, this is using your 35,200. Now, if you round those to the nearest integer using traditional rounding rules, this will round up to 29, up to 35, up to 142, down to 23, and up to 22. But if you added those all together, they add up to be 251. Well, that's not okay. You need it to be 250, which means the standard quota is not going to work. You need to go, or the standard divisor is not going to work. You need to modify the divisor. So because we were too high, we need to modify our divisor to be a little bit larger. Okay, so instead of 35,200, which was the standard divisor, we're going to go up a little bit higher. Let's try 35,250. And we're going to go through and we're going to take each population divided by that divisor to see what happens. So when you look at this slide, remember that's our standard divisor. We're using the modified divisor. So 28.46 is going to go up to, is going to round down to 28. 34.85 will go up to 35. 141.5 will go up to 142. 23.0 will go down to 23. And 21.69 will go up to 22. And when I add those together, I get 250. So I'm going to proportion those amounts to each state. So our sum of the modified rounded quotas is 250. Therefore, each state is awarded the number of legislative seats listed in the table. The last is the Adams method. So the Adams method also uses a modified divisor, but this time in the modified divisor, you're going to round up to the nearest integer. Again, you want the total of all of the integers to be the exact number to be apportioned. We will refer to this as the modified upper quota. Same example, Republic of Geranium, 250 seats. Okay, so we were previously using 200. But this time we want to be able to round up. So we need to use a larger number. So they selected 35,400 to just try it and see if it works. So when we do that, remember this first one is our standard divisor, which we know doesn't work. We're going to take our modified quota. So we'll take 1,003,200 divided by 35,400, and that's how we get our 2834, and then our 3471, and so on. But on Adams' method, you round up to the nearest integer. So don't follow traditional rounding rules. 28.34 is going to become 29. 34.71 will be 35. 140.98 will be 141. 22.97 will be 23. 21.60 will be 22. Add those bottom numbers together, see if they make 250, and they do, so then you're done. So when we used the divisor 35,400, we were able to get a sum of 250 seats. So of the four methods we've discussed in this section, Hamilton's method is the only one that uses the standard quotas. Jefferson's method, Webster's method, and Adams' method all make use of the modified quota and can all lead to violations of the quota rule. So just to summarize, you may want to print this slide out. Hamilton's method tends to favor larger states. Jefferson's method favors larger states. Webster's method favors smaller states, and Adams' method favors smaller states. Hamilton's method uses the standard divisor. Jefferson's method will use a number less than the standard divisor. Webster's method's a crapshoot. You could go smaller, it could be equal, or it could be greater than the standard divisor. And then Adams' method is typically always bigger than the standard divisor. Okay, good luck.